Okay, hi everyone, welcome to lecture 21. So last time we started talking about a new topic, proof composition. It is a rather general technique that can be used for reducing query complexity without increasing too much proof length. In particular, it is one of the approaches to proving the PCP theorem. This requires defining an outer and inner, or rather, the proof composition technique applies to two PCPs, an outer PCP and an inner PCP. The outer, we saw, needs to be robust, and the inner, in fact, needs to be a syntactically slightly different object, a PCP of proximity. We saw how these two definitions interact to give rise to the proof composition theorem. We also saw how to extend these rather straightforwardly to the case of interactive oracle proofs with the interactive oracle with interactive proof composition. And we're just basically left with the task of figuring out how we're going to construct robust PCPs and how to construct PCPs of proximity. Today specifically, we're going to talk about how to construct robust PCPs, so the outer sort of PCPs. Okay, so this is just what I said. Let's recall the definition. So here it is. This is the definition from last time. So we say that a PCP system for a language L has robustness parameter sigma if certain properties hold. Well, first, the completeness is the usual completeness for a normal PCP. What changes is in the soundness. It says that whenever you have an instance that is not in the language, whatever PCP you write down, it is the case that the probability that a local view is sigma close to accepting, okay, is small. Okay, and remember that for talking about robust PCPs, we are specifically talking about non-adaptive ones, right, that we can decompose as a query algorithm that inspects certain locations and a decision algorithm that sort of decides based upon them. And using this decomposition, you can define this kind of relation of accepting local views where you give me the instance for the verifier, the randomness for the verifier, a candidate local view indexed by the correct indices, and you ask whether the decision algorithm says yes. Okay? And this is a strengthening of normal PCPs, because normal PCPs say that the probability that a local view is accepting is small. Here we're saying that the probability that a local view is close to accepting is small. Okay? All right. So that's just a reminder. And we saw last time why, as an outer PCP, this is helpful, because it kind of aids the inner PCP of proximity. We already remarked last time that your robustness, if it is not just 0, but in fact all the way up to 1 over q with respect to the Hamming distance of the alphabet, is trivial because anyways you're comparing strings of q symbols, so anything that is strictly below the fraction 1 over q, that is as good as 0. Okay? So the question is kind of how to go above. So, and the challenge in particular is to achieve kind of a constant robustness parameter even when q is super constant. Okay, and remember that kind of everything we constructed, every PCP of polynomial size we constructed so far did have super constant query complexity. Okay, so they may have some very small 1 over polylog trivial robustness, but we're really interested in constant robustness parameters. Okay, and so. And roughly speaking, in today's lecture, we're going to show how to prove a robust analog of the polynomial size PCP that we constructed, at this point, maybe 10 lectures ago. Okay. So specifically, we're going to prove that NP has a PCP with all the usual parameters that we're used to: perfect completeness, constant soundness error, binary alphabet, polynomial proof length, polylogarithmic query complexity, logarithmic randomness. And then this new parameter we're achieving on top of all of these things that we already had. This is the extra thing you achieve is a constant robustness parameter. Okay? Oopsie. Let me first ask if there are questions about this slide. Okay? So we already seen this theorem without this part over here. And now we want to add the robustness parameter. Why? Because we're going to want to use this as the outer PCP, the one with like good proof length, but sort of a kind of not constant query complexity that we want to improve. No questions about this slide? Everything clear? Okay, great. So we're going to have a two-step plan to do that. It's going to be, we're actually going to start from scratch. We're going to basically start from the PCPs that we know, the one we already constructed. Namely, in mind, you can just think about the construction for quadratic equations that uses the sum check protocol and the Ludwig test. Okay. And here is the statement, which is basically what I wrote in the prior slide without the robustness. We want to kind of make that appear. So we have two steps, okay? The first step is going to consist of something called query bundling. So essentially what we're going to do is going to take the queries and kind of put them all in the alphabet, okay? Kind of you see kind of what happened here. We took the queries and put them up here in the alphabet size, okay? And we're getting constant query complexity. But now we have a large alphabet. Okay, so we're going to reduce query complexity to constant at the expense of alphabet size. Okay, this step called query bundling. Notice that it's not clear necessarily how to do that because queries could be all over the place. You can't just kind of gather them up in symbols. Okay, kind of we'll see later how to do this properly. And the second step, it's called robustification. It's kind of a generic way of saying, okay, well, once you have constant query complexity over a large alphabet, then what you can do is you can kind of go back down to the binary alphabet and kind of go back down to polylogarithmic query complexity, but now you're able to get a constant robustness parameter. And so when you kind of apply these two steps one after the other, we kind of get this. We're back to where we started, but we also have this constant robustness. Okay. Both these steps are kind of require doing something. They're not entirely trivial, especially the first one. And so here, as I said, we're going to achieve constant robustness over the binary alphabet at the expense of query complexity. And now we're going to study each step in turn. Are there any questions about kind of what is the high-level plan? Okay, first we're going to bundle queries, okay, kind of go a constant number of queries to a large alphabet. So think about it as essentially like highly correlated queries. You can think about it like they're kind of coming in tuples. So you can kind of allocate large symbols for them. And then you want to say, okay, well, I have some way to kind of break down the queries again, but when I break down the queries again, I'm actually not going to pay I'm not actually going to pay nothing in robustness, okay? And there's going to be something that we have to do there. Okay, so we'll actually go through, I think, robustification first because it's the slightly easier of the two, and then we'll kind of go to query bundling. Okay. Are there any questions about this slide? Again, both of these techniques kind of not only they're used, for constructing robust PCPs, things that look like these, they're used all over the place in all kinds of PCP and IOP constructions. So being familiar with kind of these paradigms of query bundling, robustification is something that, sort of, there's actually only so many techniques in the probabilistic proof literature. They just differ in specific application or which probabilistic proofs you're applying them to. So it is kind of useful to know sort of the main ones. Okay. All right, so we're going to talk first about robustification, okay, which is, again, we're in a setting where we have a large alphabet PCP, and we want to get good robustness over the binary alphabet, okay, but we want to kind of break down these large symbols over the binary alphabet, but without incurring its kind of brittleness of small queries, okay. Now, intuitively, we're going to want to break each large symbol query into multiple bit queries. And let's start with, like a truly kind of naive solution. So let's say that this is the original PCP we start from. We're kind of querying, let's say, 2 large symbols. And what we can do is we can just say, okay, I'm just gonna like think of all the bits inside each symbol, right? So here they are, like for example, there are 3 bits in the first symbol, 3 bits in the next symbol, and 3 bits in the third symbol, so on and so forth. So my kind of proof length over this new alphabet will grow by log the size of the alphabet, right? Because I need log bits to represent each symbol. And of course, my query complexity will grow correspondingly, and I will have to make kind of each of these bit queries one at a time. Okay, so this is just as a sort of a straw man to kind of study. It should be clear this preserves completeness and soundness. Okay, because like if before I was making my queries like this, I just my queries like that, and I have kind of this one-to-one correspondence between proofs. So I really preserve completeness and soundness. And also, kind of by construction, we have reduced the alphabet from a large alphabet to a binary alphabet. The problem is that the resulting PCP may have a trivial robustness that is even less than 1 over Q times log sigma. Okay, and you should think Q as being constant, but log sigma not as being constant. Okay, because we're thinking from a large alphabet. Okay, so why is that? Well, many local views in the large alphabet PCP could be maybe 1 symbol out of Q away from accepting, because we are starting from some generic large alphabet PCP. All we really know is just normal soundness that says most local views are not accepting, but we don't know that most local views are far from accepting. So they may all be 1 symbol away from accepting, like very close. And so in the binary alphabet PCP, this could translate to 1 bit out of Q log sigma away from accepting, because when you have 2 large symbols differ, it could be that they differ in 1 bit only, right? So you lose an additional factor of log sigma over that distance, right? So, without knowing anything else about this PCP, when I break it down like this, I'm going to get a kind of trivial robustness that is kind of uninteresting. In particular, if Q is constant and sigma is super constant, this ratio will give me a sub-constant robustness parameter, which is kind of not what I was hoping for. Okay? Does it make sense? All right. But actually, we can, this as simple as this idea is, we can actually fix it. We'll see in the next slide. And essentially, what we can prove is basically achieve all of the parameters that we have here. We're just going to pay for some universal constant in the proof length, in the query complexity, because here the constant was 1, right? Here it's going to be, I don't know, 10 or something, okay? But crucially, we're going to get a robustness parameter that is just 1 over Q rather than 1 over Q times log sigma. And again, we should be thinking about Q being constant because the robustification step will be applied after query bundling. So our regime is that Q is constant and sigma is like, log sigma is something like polylog, okay? So next slide, we're going to see how to do this, okay? And again, notice that how cheap we would be able to. We are able to do this over the kind of the strawman solution. We just pay a big O in the proof length and query complexity, and suddenly we're able to eliminate any dependence on the alphabet. Okay. Any questions about the strawman? And why the lemma that we're proving is proving something stronger. Okay. So, so I'm just copying here again the lemma we want to prove. The idea is that we're going to take each large proof symbol and encode it via a good code, and then we're going to require the verifier to kind of insist that symbols are part of the code. And this will essentially basically sparsify accepting local views and kind of put them like kind of far away from one another. So let me turn this into something more precise. So first, let enc, which maps a symbol to a string of bits, be an injective map with so-called, here I'm using coding theory terminology, but I'm also going to explain what it means, constant rate n, so n is the number of bits that come out. And when do we say that the constant rate, okay, this is not really the rate, is let's say linear block length. maybe let me call it linear block length. The rate is the message length over the block length. So here I'm talking about the block length n. So n is the number of bits to encode a symbol, and it's just going to be, I don't know, 10 times log sigma or 100 times log sigma, you know, thereabouts, okay? So that's why the ratio of like the encoded message, of the message over the encoded message is constant, okay? So that's why we call this constant rate or linear block length, okay? And also, we're going to need a constant relative distance. What does that mean? It means that if you take any two different messages, what are messages? Well, two alphabet symbols, okay? And you encode them, now you're going to get two n-bit binary strings, and you look at the fraction of locations at which they differ. And they differ in, say, I don't know, 10% of the locations. So namely, as long as you have two symbols that are different, and in their binary representation, they may differ in 1 out of log sigma locations, out here, they're going to differ in 10% of the locations. So it kind of amplifies this 1-bit difference into like a constant fraction of differences, okay? All right, and you know, this is basically a standard tool. It's known as a good code because, you know, the output is over a binary alphabet. It has constant rate, constant relative distance. Is known as a good code. It can actually be constructed via code concatenation. If you want to kind of check it out on Wikipedia, like the construction is called Justice encodes, and it's pretty simple. It relies on an outer Reed-Solomon code and an inner brute force sort of code, and it's kind of pretty similar to like kind of proof composition, as I mentioned in the past. So we're just gonna, you know, take it as a given because, you know, there's plenty of these things to go by. So what are we going to do with this? So what we're going to do is now we're going to take each of the symbols we started from and we're going to encode it. So rather than getting maybe 3 bits, maybe we're going to get 6 bits for each symbol, okay? So 6 bits for one symbol, encoded symbol, 6 bits for another encoded symbol, 6 bits for another encoded symbol, right? And you see now that my proof length kind of blows up rather than by log sigma, by n, and my query complexity rather than by log sigma by n. And what is n? Again, you know, 10 times log sigma, right? So that's, you know, the big O where it comes from here. So more precisely, the prover will kind of compute the honest PCP over the large alphabet. It will encode each symbol and output a concatenation of all those bits as an n times L bits. Okay, so that is how you produce this one. Now, crucially, what will the verifier do? Well, the verifier will just run the old verifier, and the way it will answer a query, it will read a block of bits, in this case 6 bits. It will check if they are in the code, and if they are in the code, it will just take the inverse map. Okay, and right now it doesn't really matter how to do this efficiently. If the code is linear, all of this can be done in polynomial time using so-called, you know, parity check matrices and the inverse of the generator matrix. So it doesn't really matter right now. The point is that, you know, because it's an injective map, an inverse is well defined, and so we can sort of reply, you know, each question by reading a block of bits, checking that they're in the code. If they're in the code, there is a well-defined symbol that is associated to it. You invert the map, you get the symbol, and return back the answer. Okay? So kind of, yeah. So this is the construction. Now completeness. Look, if x is an L, then we know that the original verifier, you know, will accept with probability at least, say, 1, or 1 minus the completeness error. It will accept the honest one. And if I encode the honest one, well, because I always answer with the inverse, I am running basically the original PCP, so I'm clearly preserving completeness. Okay? So for robust soundness, well, that's going to need, I mean, it's not one line. I'll need, you know, one slide for that. Okay? And so we're going to discuss robust soundness in a moment, but, you know, are there questions about syntactically what we're doing, or, you know, what is a code, those type of things? Notice that just breaking down a symbol into bits is like a terrible code, right? You know, it has rate 1, okay, so you don't add redundancy, but it has relative distance, 1 over log sigma, which is subconstant, okay? And here we're just basically, so that's kind of a trivial encoding, and here we're just saying, let's just pick a better encoding to break down into bits. We're gonna, rather than having log sigma bits, we're gonna have 10 log sigma bits, but in return we'll have, I don't know, like 10% relative distance, okay? So in some sense, this is a generalization of the prior approach that lets us, specify any encoding procedure that we want. And before it was just kind of the identity encoding procedure. Okay? Are we clear with the construction? All right, so what we're going to prove is that the robustness is, in the order 1 over q, but specifically it's going to be a delta over 2. Well, delta, was the relative distance of the code. Delta over 2 is known as the unique decoding radius, and we'll see later how we use this, times 1 over q, okay? And because the relative distance is constant, this entire expression is, order of 1 over q, okay? But here, I just kind of made explicit how the code affects it. All right, so let's prove the robustness property. So we need to consider an instance that is not in the language, and we're going to fix some malicious string of bits. How many bits? Well, n times L, right? These allegedly are kind of n blocks of bits, each of which is in the code, right? Allegedly, but we don't know, right? Let E be the event that the local view contains a string that is delta over 2 far from the code. Now, just to be precise, when I look at the local view, I'm going to have q blocks of n bits, right? Because I'm going to be reading q symbols. Each encoded symbol will bring me n bits. So when I say contains a string, I mean one of those blocks, right? I don't want to say block because it suggests that we're working over a different alphabet, but we really are working over binary strings, right? So we're going to define E to be the event that one of the q strings, one of the q binary strings happens to be pretty far from the code, okay? From a valid sort of code word. Okay, so let that be the event. Now we are interested to study this probability. Do we agree? Right? We want to kind of look at the local view, a random local view, and we want to compare it, how close is it in a binary Hamming distance to some accepting view, right? And we want to argue that the probability that it is smaller than this kind of magical quantity, which is the unique decoding radius times 1 over q, is small, right? So we want to upper bound this probability. Are we clear that this is kind of what we want to do? And remember here, this kind of capital delta here is measuring binary Hamming distance. And this is a string of qn bits, okay? And here we're comparing it against strings of qn bits that are accepting. In particular, the strings of qn bits always consist of strings that are all in the code, okay? Because the verifier checks that. All right, so we're just gonna upper bound this probability by saying it's certainly at most the probability of this event conditioned on on this kind of bad thing, conditioned on this event E, or plus the probability of that bad event conditioned on not E. Okay. I'm not using any properties, but sort of this discrete probability. And now I want to argue that this first term is 0, and this other term is epsilon s, okay? Why? Because we wanted to argue that this probability is at most the soundness error for the robustness, which in the prior slide I was claiming was epsilon s, okay? So let's argue that this first term is 0. We say if this local view contains some block of n bits that is delta over 2 far from the code, then we know that this kind of, when you kind of look out and you look at the whole local view, it must be at least delta over 2 times 1 over q far from any accepting local view. Why? Because all accepting local views consist of q strings in the code. So kind of in the worst case, it could be that this string that was far was the only string that was far, right? So, and all other strings are actually in the code and they contribute no noise, right? So like in the end, this one is over q times n, right? Because we're counting the number of locations over the whole local view. So we know that this thing is going to be far, and well, if it is far from all accepting local views, then this event is just not going to happen, okay? In sum, because all local views consist in particular of q blocks of n bits in the code, if even one of those strings is this far, then the whole thing must be at least this far. So yeah, okay, so that's what we get, okay? Notice that so far I haven't used in any essential way the unique decoding radius. I'm just saying if I have some quantity here, I will get some quantity here times 1 over q, okay? But I haven't used the fact that it is like a special quantity, okay? Of course, then because this quantity is specifically the one that appears here, I get a 0, but this is all just syntactic. I haven't really used the unique decoding radius. So that will come in the second part, but before I get to the second part, are there any questions about the first part? You should ask questions, okay? Because otherwise I'm going to keep breezing through slides and I don't have time to digest them. Okay, so let's talk about the second term here. We want to argue that where the local view only contains strings, each of them that are closer than unique decoding radius to the code, okay? So in this case, we're going to define a so-called correction, okay? So we're going to, not in this case, with this I can always define it, so let's define it here because I don't need it in the other case. Given this arbitrary proof, I can define its correction. I'll kind of change the tilde to a bar to be the string where the string of n times l bits, where every string of n bits is in the code, and which code word I pick is the closest one, okay? And if there's multiple ones, you just break ties arbitrarily. Anyways, when you're close enough, there won't be any ties. And I'm going to call its decoding with this, small pi bar, okay? Which I can just then take here in a well-defined way the inverse encoding, okay? Again, this is just a definition that is kind of standalone. It's under the scope of item B just because that's where I use it. Given any string like this, I can correct it and just say, okay, on this string there's some noise. Just take the noise away, take the noise away, take the noise away. I get a bunch of kind of honest-looking encodings. There may or may not be accepting, right? That's a separate story, but just syntactically, they are all in the code. And once I do that, I can actually decode and recover like a PCP for the original, some PCP that may or may not be accepting for a certain randomness for the original proof system, right? This is over the large alphabet. Okay, and this is just a definition. Any questions about the definition? Okay. So look, by the soundness of V, the probability that I run my kind of new verifier given this corrected proof is the same as if I run my old verifier with this kind of inner proof system, inner PCP. And because we are in the no case, in the soundness case, this probability is at most epsilon s, right? But notice that this is not what actually happens, right? What I'm running is I'm running this verifier on the original, not the corrected one. Okay, but here I'm telling you that to the extent that you see the corrected one, you can't accept too often, even on the corrected symbols, because we are in no case. Okay. All right. now we are in the case, now we can start looking at B, where now I look in the local view, say for a particular row, and every string is closer than unique decoding radius to the code. Okay, so kind of the prover decided to try to fool me by writing a bunch of code words and adding a little bit of noise on each one of them. Okay. Then I argue that pi bar restricted to this local view. Okay, this like their correction restricted to this one is the only string of Q code words that is this close to this kind of noisy set of strings. Okay. Why? Because look, each of these guys has a unique closest code word. Why? Because we're within a unique decoding radius. Remember, what is a code, right? Is a bunch of code words that are at least delta away from one another. Okay? If pairwise every two code words are at least delta away, it means that if you are within delta over 2 of some code word, that code word is the only thing that is closest to you, right? That's why this is called unique decoding, because you can be decoded to a unique code word. Okay. Now, because each of these symbols is close, is close to the code, then these symbols that we decided upon in advance, specifically restricted to these, are the only ones that are this close to these guys, right? Notice that there's a loss here because it could be that in the worst case, all of these are perfect code words but one, right? And it's the only one that contributes distance, right? And so we're this here when I'm delta over 2 close, it doesn't tell me that all of the distances are exactly delta over 2, right? I don't know. I'm just saying that all of them individually are delta over 2, but it could be in the worst case that there's a little bit of distance in just one symbol and all the others are perfect. So this is all I can conclude. Okay. Okay, but if that is the case, the probability that I want to, the probability that I want to study, that is this one here, condition on this event, E bar, okay? And E bar is, we are in this condition, is bounded from above by the probability that pi bar is itself accepting. Why? Because here we're asking, look, what's the probability that this noisy local view is close to an accepting one? Now, all accepting ones are code words, okay? And the only closest code word is this one, right? So the only candidate that I need to consider is this guy, and I'm wondering whether this guy itself is accepting, right? But by definition, that's just like running the verifier on the corrected code word, okay? And so that's and we already argued that this one is at most epsilon s, so we're done, okay? Anyways, there's nothing too deep going on here. Just I kind of try to write out explicitly in a verifiable way that all the steps, but intuitively, because the verifier has kind of sparsified the local views, when you're kind of close enough to an accepting view, that is the only accepting view you can be close to, right? And that accepting view, kind of corresponds to the soundness data of the original proof system, okay? Because it's in the code, okay? And yeah, so this is the kind of end of the robust soundness proof. Are there any questions about this argument? Hopefully it's kind of explicit enough. Okay, so this is the end of robustification. Again, what we've done is we have used a code to take a constant query, large alphabet PCP, to bring it back down to binary alphabet, more queries, on the order of log sigma queries. In our context, is going to be polylog. But now we have, constant soundness error, okay? So constant robustness. Why? Because we have delta over 2q, q was constant, delta was constant, the whole thing is constant, okay? Great. Bundling queries. Okay, so this is the first of the two steps. We just talked about the second one. Now we want to say, okay, we start with a binary alphabet a super constant number of queries, and we kind of bundle up the queries into larger symbols, so we have a large alphabet and a constant number of queries. Okay? Right, this is just what I said. And intuitively, we're going to construct, a new alphabet that is, in the order of the original alphabet, to the Q. Okay, we're going to have some small loss there, but that's okay. And again, we're going to restrict our attention to non-adaptive PCPs, so it can look like that. And so let's actually start with something simple. I think this was even something that was in a homework. I think maybe in the second homework. So, and also I will not give the proof because you've already kind of worked on it, but at least I can state it. That this first strawman is to say, okay, well, let's just consider all possible query sets. They're kind of correlated tuples of some sort across all randomness choices. And I'm just going to kind of lay them out into like one big symbol after another. Now, they may be inconsistent, right? Because these tuples are going to overlap. And so I'm going to keep around the original PCP and kind of do one random consistency test for the tuple that I choose, right? So in more detail, kind of my new PCP looks like this, my original PCP over the small alphabet. And then, all this kind of teeny tiny sort of Q tuples of symbols that I consider as like one symbol at a time. And I have 2 to the R of them, right? And in the honest proof, this restriction is going to be the whatever selection of queries from that one PCP, right? And the verifier is pretty simple. You just pick a random choice of randomness, and then you pick a random number index of the query for consistency check, and you read kind of this entire symbol. You read one location here, this location, the jth query in this tuple, right? The jth index in this tuple. You're gonna do the consistency check. You're gonna check that the jth location inside here is indeed corresponding to the correct location in the original PCP. And then I'm just gonna run the verifier, assuming all the other queries are also consistent, and I'm just gonna answer the jth query with whatever is the oopsie, so I guess J here is overloaded. I'm going to just put here J bar or something. that is not the J that I selected. It is the J that I iterate over across the J queries. Hopefully that's clear. And in the homework you already analyzed this thing, and basically these are the parameters you get out. First, as expected by construction, your alphabet goes up. You have 2 queries because you have one query here and another query here. Your randomness goes up a little bit. That's fine. Your proof length increases a little bit. That's also fine. The thing that is kind of annoying is the soundness error, right? This was the expression that you showed in the homework, that if your prior error was epsilon s, then your new error is 1 minus epsilon s times 1 over q. In particular, this doesn't suffice for us because we need constant soundness error even when q is super constant, okay? So if, for example, q is, let's say, log n, then we're going to get something like 1 minus 1 over log n, which is not bounded away from 1, okay? So this is not like a constant soundness error, all right? So this transformation is helpful to go from some constant number of queries specifically to 2, and it is used, this transformation, for going to construct 2 query PCPs. But it won't help you to go from a super constant number of queries to a constant number of queries, okay? It's just not the regime where you want to apply this transformation, okay? Is it clear? Okay, but I reminded you of this strawman because it actually forms a template, just like in the prior step, of something better, okay? And we kind of need to fix this kind of crappy soundness error, and so we want to sort of be a bit smarter about the way we bundle up queries. So we're going to start, using Ludwig extensions, okay? So let's introduce a field, a subset in the field, and some number of variables. This will be determined later. And also we'll make some assumptions on the field size. First, we want to be able to at least represent an alphabet symbol in the field. So that's pretty natural. And Also, we're going to assume that the field is at least the query complexity. This is not inherent. It is more primarily for convenience. So we're basically gonna low-degree extend our original PCP. So because our original PCP has L locations, we're gonna identify it with our friendly and familiar hypercube here, h to the m, by setting m, the number of variables, to be log L over log of the dimension of the cube, right? The side of the cube. Okay, so this is kind of the usual setting of parameters. And we can view now a query set as q elements in this hypercube, right? Because before there were indices in 1 through L, now I have kind of relabeled 1 through L as the elements of this hypercube. So now queries are just elements of h to the m. Okay? Now we're going to make two changes from the prior approach. The first thing is we're going to replace the kind of the reference PCP with its extension. So this is going to be the reference, all right? Kind of the non-bundled part of the proof. And this is just normal logic extension. And secondly, instead of carrying around a tuple of queries, we're going to take our extension polynomial of the proof, and we're going to derive a polynomial that remembers the answers to all the queries we care about in a query tuple. And what is this thing here? This thing is a polynomial, okay? This is a polynomial that interpolates the indices of the queries. So basically, for convenience, let's just say that we have q. This is where I'm using this part here. Again, it's not very important. Let's say that I'm just calling 1 through q distinct elements in the field, and I'm just going to associate the value of this polynomial at index 1, 2, 3, 4, 5. And again, we're fixing a particular PCP randomness. Is going to be the jth index of this tuple. Okay, I'm going to get some polynomial of degree less than d, right? Because I'm interpolating q things, I get some univariate polynomial of degree less than d. Now, remember that the output of this one is not just one field element, it's m field elements. So this in fact is a collection of polynomials. Because remember that in each, like pi hat takes m variables as input. So I'm plugging in here m univariate polynomials. So you can think about this as some sort of manifold, okay? It's like a curve, right? It's like a line that moves in like f to the m, okay? So it's kind of threads. It's a line in the hypercube that kind of threads through all of these indices in the hypercube, okay? So kind of pictorially, if it could be called like that, right? If you have kind of, these are your questions, right? I'm just going to take a univariate, like a collection of univariate polynomials that describe the, as curves, each of the m variables of this curve, right? And I'm going to take I'm going to compose that with this one. I'm going to get a univariate polynomial of a degree, that is the total degree of this guy, which is mh, times the individual degree, the only degree of this one, which is q, so qmh. So now I have here a univariate polynomial that remembers at location 1 through q the answers corresponding to the answers to the queries 1 through q of this particular tuple. Okay? So I'm kind of bundling together the answers in a very particular fashion. Okay? Okay, so what am I going to do with that? Well, first it's clear that, I'll just lay out, instead of my reference PCP, I'll have its logic extension, and instead of the tuples of queries, I will have basically extended tuples of queries. Okay? Now notice that I could have, of course, extended the actual tuple directly, but that is exactly what I'm not doing here. I am specifically choosing to be not just the unique logic extension of the tuple of answers, but to be this composition. Okay? Why? Because it will help me with the consistency check. So for now, I call this a warm-up because I'm not going to worry about what happens if this guy is not a logic extension. I'm just going to ignore that for now. We will need one other idea to kind of deal with noise. So let's not have any noise around. So the new prover and new verifier work like this. Well, the prover just prepares all this stuff. So it prepares the prior PCP. And by the way, what is the prior PCP now? It is some string that maps h to the m to f, right? Because before it was L to sigma, but now because we embedded sigma into f and L has become h to the m, this thing is a function from h to the m to f. I extend it, I get pi hat, and then I compute all of these composed polynomials and I output this whole bundle. All right, I'm just kind of saying how you compute this. What are we going to do now? Well, like before, I'm going to sample a random execution of the original verifier and then some randomness for my consistency test. Now before, my consistency test was a random index between 1 and q. Now it's a random field element. Why? Because I'm going to read, again, this whole thing here, like the coefficients of the polynomial. I'm going to read this location, and I'm going to check that this identity holds. That's my consistency. Okay? And otherwise, if the consistency holds, I'm just going to read out, and again, okay, now I can use J, it's fine. I'm just going to read out kind of the answers corresponding to the queries, right? So let's look at intuition here before we analyze it. So we have this identity test. I'm trying to establish, is it the case that this univariate polynomial of degree QMH is identical to this composition, right? Where again, notice that pi hat specifically appears here. That's why I'm querying it here at location. I'm querying it at location q rho gamma, right? This, if they are different polynomials, I will catch this with high probability because these are low degree polynomials. And if they're the same polynomial, that means that it is safe for me to read out all of these locations because that's exactly how I constructed it, to kind of tell me the answers of pi hat at each of these locations, right? So I'm kind of, exfiltrating the answers. Now, that's not really surprising, is it, right? Because kind of the description of this guy is at least q, right? So it really does remember all these things, right? And it just kind of has them all inside, okay? And, this is just like, some trick. I was specifically not interested to query this one at many locations, and instead I just ask kind of these tuples, but now I have like a stronger test. We need to argue that it's stronger, by the way, and we're going to do that next. But are there any questions about this slide?
What should we think of the field size as here?
The field size will be, well, at least QMH, okay? Because we're testing things that are QMH. And in fact, 100 times QMH will be fine, okay? And if somebody really cares about field size, we could even have not paid really for Q here, because instead of considering like a kind of a univariate curve, I could have considered a multivariate curve, and you would have had a cost here that is more like log Q, the total degree. So like kind of, the fact that I embed a symbol in one field element, that I'm really using it, but this Q here is just because here I'm just using univariate extensions. I could have used multivariate extensions. It's not super important. Anyways, Q is not that large. So we should think about it as polylog. Right? Thanks for the question. More questions? So it's good we've seen log extension many times, right? We'll start using them in all kinds of new places, right? Okay, so now we need to argue that the soundness error of this construction, which again, we're still in this fantasy world where we don't have noise. We need to argue that this construction has a decent soundness error. So let's argue that. So here I just copied the verifier, dropped the prover because it's clear what this is. And we're gonna look in the warm-up case where pi hat is guaranteed to be a log extension of something. We can prove that the kind of factor of 1 over q, which was subconstant, now is replaced by 1 minus qmh over f, okay? Which, as f is, let's say, 10 times qmh, this is a constant, independent of q, right? Now, intuitively, like, what's the intuition here? This is saying that, when the tuple is inconsistent, you have a probability of 1 over q of catching it. And here you have a probability of 1 minus this over that. And, that's basically like the number of zeros, the number of sort of locations at which the test could fail. And analysis is kind of pretty similar to the way you kind of would analyze this one over here. So I'm just gonna not go through it, too carefully. But so fix some instance that's not in the language, pick some PCP that satisfies the fantasy world, but otherwise it may be inconsistent. And we're really interested in understanding the probability that the verifier accepts. This is the same. I mean, I'm opening up the construction, right? This is the same as when I run the verifier, which you can think about it as the decision predicate on this tuple evaluated at 1 through q, and the consistency check at gamma passing, right? Well, that is 1 minus the probability that either of these things fails, right? And it's pretty easy to argue that basically, how often would this fail? Like, so there's only so many locations where these are going to be inconsistent, right? And fail and pass, right? So if the underlying polynomials are inconsistent, then we're going to catch this with this probability. If they're consistent, then we're going to at most accept it with this probability, right? We're going to reject it with at least this probability. So if you kind of do this carefully, these two things multiply, and that's the same argument that you do here. And that's it. And again, like the 1 over q is exactly the analog of like this 1 minus qmh over f. But how do we handle a case where pi hat is noisy? This is actually non-trivial, okay? And since I've breezed through these slides, let's see if there's two problems in the noisy case. Let's see if you guys can find them. So let's say that now I have some noise and I'm running this thing again. What is my issue going to be? Well, first I need to make sure there isn't too much noise, so I need to run what?
Some proximity check.
Yeah, some low-degree test of some sort. Now, what type of low-degree tests have we seen in this class? Do they work over large alphabets? Not really, right? I mean, they don't have, they're just making some polylogarithmic number of queries, right? Or rather, you ask total degree number of queries, and our total degree here is mh, right? So that's like super constant. So that's out of budget. So we can't use a low-degree test. It was a bummer. But let's say that somehow we did use it anyways, and we know that there is, 10% noise at most. What's another problem?
The queries could be biased.
Right, the query could be biased. In fact, we almost certainly know it's biased, right? So for example, imagine like in a very simple kind of dummy polynomial. Let's say that let's say that this polynomial, what it does with gamma, it just squares it, okay? So now suddenly the approver knows in advance that you only query a square as opposed to a non-square, right? And in general, this thing is going to be some high degree, not high degree, but like reasonably high degree polynomial is going to have super constant degree, right? And so this is going to be in some sense like a super constant bias, okay? That might be like really concentrated in like in a small number of points. So these are pretty annoying, okay? Like how do we even make sure that we have a small number of tests? And then how do we kind of unbias this one? And in the past, the way we unbiased things is we did self-correction right? We did it for linearity testing, but you did self-correction in your homework. And again, that's like a super constant number of queries. So we're kind of really stuck here. But okay, we're going to unstuck ourselves, with one idea, and basically the other idea, I can't fit it in this lecture, so it will be like a bit of a magic hat. So the way we handle these is first, well, we're going to rely on a large alphabet constant query low degree test. Okay, such things exist. They're sort of much harder to analyze than the one we've seen. Here is an example of a statement. This is called the line versus point test. And actually, it's not just a low degree test, it's a proximity proof. So fix the function f that you want to test. Also, the proximity proof is going to be a so-called a lines oracle. Okay? Intuitively, in the completeness, so here I'm just writing the soundness, but in the completeness, the lines oracle is just the restriction of f to every possible line treated as a large alphabet, right? So how do you specify a line? Well, you give me the polynomial of degree d, univariate polynomial of degree d, that is across that line, right? Because if you take a multivariate polynomial of total degree d and you restrict it to a line, you will get a univariate polynomial of degree d, right? And you can just give me those d plus 1 coefficients all together as a symbol. And you can do that for every single line there is. Okay? So, and now we're going to have a test that's going to use the original function and this kind of helper oracles. Okay? Because these helper oracles are here to help us test the function without querying the function at multiple points. Okay, or at a super constant number of points. And a test is as follows. It's called line versus point because that's exactly what a test does. We're going to sample a random line, okay? And we're going to compare whether that line agrees with the function at a random point on that line. Okay, so here see that I'm querying the original function at the line location mu, and here I literally look up the line and evaluate it at mu, and I see, are they consistent? Okay. And the amazing fact here is that there are some actually very strong parameters you can prove, but here we don't really care about those very, very good parameters. We just care about kind of constant relationship. If f is delta far, then kind of regardless of which lines you wrote down, and again, you don't have to low degree test the lines. The lines are written as d plus 1 coefficients of a univariate polynomial, which I can read as a symbol, right? The probability that this test passes is bounded from above by some constant, okay? And in fact, these tests even have subconstants on the error. They're incredibly sort of sound. Also very hard to analyze. But we're not going to analyze it today, so we don't have to worry about it. We're just going to take it as a given, okay? Just do know that there are large alphabet constant query low degree tests, and they look natural. And that's a proximity proof. Any questions about this statement?
Not about the statement, but more so about the proof. Can you offer sort of any intuition or sort of general direction on how we would go about showing this?
Yeah, I mean, the proof is you basically study so-called inconsistency graphs. You basically write out some sort of abstract graph that kind of keeps track of which of these things are consistent, and you try to argue that if there are certain kind of large cliques in this graph, then there must be like some global consistency. Okay, so that's kind of the approach in technically, but intuitively it's kind of clear what's happening, right? So look, we know this line is low degree. So well, first we already know from the past that a multivariate function is low degree if and only if all its lines are low degree. In fact, this thing holds robustly. We also know that a function is close to low degree if and only if most of its functions are close to low degree, right? Now, on the right-hand side here, we have an actual low degree thing, right? So let's just fix for a given a and b, if for most mu's this consistency holds, it means that this line is close to low degree, right? But here we picked like a random line. So this test is basically asking, are most lines close to low degree? That's exactly what it's testing. And intuitively, we have already kind of proved that's the case, Okay, it's just that this one just syntactically different, and yeah, but intuition should kind of be there, I hope. Okay. More questions about the statement? But if you're looking for, I don't know, still like some class project of what to read up on, I mean, looking at these logic tests are excellent sort of technical things to look at if you like combinatorics. They're primarily combinatorial proofs. All right, fine. So there we have it. The other one is an idea that will actually kind of work out. Is actually in retrospect not that difficult. We're going to randomize the query itself, right? So we had this kind of unique logic extension of the Q locations we're interested in. We're going to add a point V, or rather a value V, and we're going to just bump up the degree by 1 and require that this polynomial at location Q plus 1 equals this random value V. Now, the prover will actually have to supply us with all this extra, all the possibilities of V, but if I interpolate kind of Q fixed things and I add a random point to interpolate over, one evaluation of this thing will be random, okay? Okay, well, that's it really. So here's the final construction. The prover is going to extend the PCP. Then it's gonna, rather than providing these bundles for every row, it is provide these things for every row and every choice of value. And now I have this kind of randomized logic extension with this extra point, this extra target value. It's like a random index, you can think about it, right? It's going to provide the lines oracle, right? So these are all the so I have a multivariate polynomial, I restrict it to a line, I get a univariate polynomial degree D. And I output this whole thing, okay? So there it is, okay? And what will the verifier do? It will, first it will run this test. So it will sample a random line and a random point of that line and check that the line at that point equals that point on the line with respect to pi hat, right? So this is kind of these queries over here. It will run the consistency check. Now it will sample a random row, V and gamma, and it will check this is the case. And crucially, the output of this inner polynomial will be randomly distributed in the domain of pi hat, okay? And then it will actually run the original PCP finally because now these tests have passed, then it knows it's okay to do that. And we're not going to do it because we kind of did enough things today, but it's not that difficult. In fact, it's straightforward to prove that a new soundness error is this one. How do you argue it? Well, either the prover wrote something that is far from low degree, in which case you pay for this and you go home, or he wrote something that is close to low degree and you pay the prior term minus a discount or a price of the distance, right? Because when you're running this noisy polynomial identity test, if you have some noise, then you just have to take it out from your success probability, right? So all of this should look very familiar because we've done similar analysis before. And what you get is this actual statement where the soundness error can be constant, okay? You have to pick F to be kind of big enough relative to QMH. You pick delta yourself to be, 1 or 100 or something. This entire thing is going to be a constant. This is going to be a constant. That's going to be a constant. This whole thing is going to be a constant. And now what we've done is we have obtained, how many queries? We have 1, 2, 3, 4 queries, total of 4 queries, a larger alphabet, but it's okay. This is polylog, right? The proof length here is going to be polynomial in size because of the way we set parameters, the usual way for logic extensions. And this is how we bundle queries. And by the way, if we are in an IOP, bundling queries is even easier because I don't need to ask the prover to supply me with these things in advance, either this one or that one. He can just provide them during interaction. So you really just pay for the original thing. And this has been used to construct, for example, IOPs where you have the proof length depends only on the witness, and there is like a one query to the witness, and everything else is just messages. So again, this is just pointing out these techniques are fairly versatile, and they lead to kind of variety of implications. One of them to us here is the other step in constructing robust PCPs. So going back to over here. So we first talked about robustification, which was breaking down large alphabet over large alphabet symbols using a code, so that after we break them down, thanks to the code, we have a constant robustness, 1 over q, but q is constant here. And then after we saw query bundling, how to kind of take a super constant number of queries, put them in large alphabet symbols, but because of consistency problems, we couldn't afford like losing a large soundness error, so we had to introduce these logic extensions and consistency checks that are more robust, so that we don't lose in the soundness error here, right? And along the way, there is one piece that we didn't analyze, but you're welcome to kind of read up on it. Is these sort of large alphabet logic tests. But there's a variety of them out there. There's line versus point, line versus line, plane versus point, plane versus plane, cube versus cube. All of these kind of behave a little bit differently in terms of how tight we're able to kind of approve them, especially when you want to not just look in a constant regime, but we want to understand what happens in the kind of in the beyond unique decoding regime. Yeah, so this is probably a good point for me to stop the recording.